We're doing correlation. This is what some of these things are used for. If you go to My Open Math, we want the credits, fall, and spring. And this is the way that they determine how many English classes to have. How many people took English the first semester and need to take English the second semester, and so forth. So they're looking at the relation between the fall credits and the spring credits, and they're trying to estimate the number of spring credits from the fall credits. Going to make a scatter plot of that, and when you do it this way, if you mark the data, whatever column is first becomes the X. So mark it, insert, and there's the graph, and this shows the relation between those two things. And if we do the correlation between them, equals CORREL, mark one, comma, mark the next, and it doesn't matter which one is first. It doesn't care what you call X or Y. The linear correlation between those two is 0.8, which is pretty good. I'm going to put a trend line in it, pick a spot, one of the data points, right click, and add trend line. So that they would go on the x-axis, find a number of credits, and then go up to the line to see what the spring credits might be. And the line is it isn't even, but it fits those pretty well. So that if you look at 10, there's about 10. 10 credits fall, 10 credits in the spring. Down here at 4 credits in the fall, it's like 5 credits in the spring. If you go up to the other end, 18 credits, they're looking at 16 credits. So generally it's a little bit less. But look at the line and the points. There's two groups in there. The lower group and an upper group. The lower group are these three. And the upper group are the others. This actually represents two kinds of students. The more full-time students are in the upper group. They're taking more hours in the fall and in the spring. And down here is a group that is part-time, perhaps. But we've got two definite groups in there. If we redo the graph, and this time, and there's data down here, it's split. This is the upper group. And I'm going to put in a plot for that. Insert. And if I look at that group and get the correlation coefficient for that upper group, the correlation there is 0.89, 0.90, which is higher than it was for all groups together. I'm going to add a trend line in there. And the line fits those points better. And the correlation is higher. Now I'm going to add the lower group to that. Add a series. And right-click in the graph, and you get a menu list, and select data is on there. Going to add, and we can label them or not. X values here. Y values there. And now I've got both groups graphed together, and I'm going to put another trend line on it, on this lower group. They're separate series now. And calculate the correlation coefficient between the fall and spring in the lower group. Equals CORREL. First, second, and the correlation for the lower group is nearly perfect. So when I separate those two groups, I get better relations, better correlations in both of them. Because the original one was trying to fit all those points at one time. So this is one use for correlation, is to separate groups and to look for groups. And there is a whole area of analysis that basically separates things into groups and trying to find patterns in groups. So that this is one of those things, and it works really well. It's called factor analysis. What they're looking for is what factor determines what group something goes in. And if we ran the typical factor analysis on this, it would bring out those two groups. So that's one use of this, and it's very common. It's like you go to the grocery store, you got a Kroger card or a, Food Lion. You scan your card. They use that to look at what you are buying and what you might buy next. So that they have you in there. They don't know it's you, but they know that whoever buys this thing tends to buy that. And they will start spitting out coupons for exactly that. And they know what to stock in the store, so that they know the demographic. All right, go back to My Open Math, and we want the car mileage, type, and value. And you may as well keep the other one because we're going to go back to it. And in this one, we want to know what affects the price more, the age or the mileage. So we're going to get the correlations for age and miles with value. And we're going to do this in a different way. Go to the Data tab. And have you got Data Analysis up on the top menu? If you don't, we need to go back to File, Options, reload that. If you click on Data Analysis, in the menu, there is one for correlation. Click on Correlation, make sure it's highlighted, and do OK. it wants one thing. It wants input. And we're going to mark everything, including the titles, miles, age, and value, all the way down. Since I included the titles of the columns, I'm going to click Labels in First Row. This is going to put information there that'll tell me what the variable is. Otherwise, it just says variable 1, variable 2, and so on. And then the output range, just pick a spot that's convenient. And then OK. This calculates all possible correlations between the variables. We had 3 variables. We've got a correlation between miles and miles, which is 1 because it's the same thing. A correlation between miles and value, minus 0.69, minus 0.7. Miles and age. Miles and age are correlated, but not very well, about 0.5. But miles and value, age and value is at 0.59. So which one affects the price more? Age or value? Which has got the higher correlation? Given that it's negative, the more negative correlation. The miles has more to do with it than the age. And in fact, this is what the car dealer is looking at when you take a car in to trade it or something. They want to know the mileage first, and then they'll get to the age. They tend to be related, but it's easier to sell a car with fewer miles. So this is a way to separate those two groups again, and factor analysis does this kind of thing. It's got a different scoring system, but it's basically the same thing. So with the correlation, we can separate these things out and see what is going on. Go back to My Open Math and into correlation and scroll down. There is a criteria for significance for R. R is a mean, just like any other average that you calculate. It represents a population parameter called rho, a Greek letter that looks like a P. But we can find the significance level. The test for the significance of R is 0 or not. We never test for a particular value. It's either 0 or it isn't. Is it significant? 0. If it is, it doesn't matter how high it is. If it's not, doesn't matter what it is. The problem with this is that as you get more and more observations, the significance level, the value required, gets smaller and smaller and smaller. And if you look in there, there's statistical significance of R. There's a link there to a significance table. And for 10 observations, it takes an R of 0.6 to be significant at the 0.05 level two-tailed. As you get more and more observations, it gets less and less and less, until by the time you get to 100, it only has to be 0.2. 500 is 0.09. That isn't even a correlation value, hardly. But it's statistically significant. And it is completely useless because of the sample size problem, and The correlation coefficient has more to do with what you are studying than it does with any significance level. If you are dealing with people or economics, sociology, you're going to get a correlation coefficient of 0.3 as the highest you'll ever get. If you're dealing with natural phenomenon, I was dealt with fish, with trees, with deer, with something physical. And if you look at the correlation between fish weight and fish length for a particular species of fish, if it isn't 0.9, you think you made a mistake. So that the significance level of R is almost a joke. It's much more important as to what you are dealing with. Look at, in MyOpenMath, we're going back to that data, and it's in the outside correlation and regression, and we want edited health data. There it is. It's the last one on the list. And this is data, it's edited health data because I took out a bunch of stuff and converted everything into values. And it's got in the data gender, age, systolic blood pressure, diastolic blood pressure, cholesterol level, height, weight, body mass index, and whether they are a smoker, diabetic, and health. If the health is 2, that means it's good. If the health is 1, it's fair. If the health is poor, it's 0. I can only handle numbers, so I can't use good, fair, poor, whatever. I have to have a value. So for smoker, they are or they aren't. Diabetic, they are or they aren't. We're going to do the same analysis with the correlation for these variables, using all the correlations together. So back to data and the data analysis tool pack. We're still on correlation. And in some versions of Excel, it keeps the last thing you did. So you have to erase the pieces out of it. But for the input range now, I'm going to take everything from gender across to health and all the way down. And there are 299 observations. The original data set had 1,000 and some, and showed basically the same thing. So I've got all the data marked. Go back. I want to make sure that labels in first row is marked, so I know what variables I got. And the output range, doesn't matter where you put it. I'm going to put it back up toward the top just because. And OK. And it shows all the correlations between each variable, 2 at a time. And I'm just going to knock decimals off of here. Look at the correlations in there. How about the correlation between smoking and blood pressure? You would think that that would be a high positive correlation. If you smoke, you've got high blood pressure. Here's blood pressure and smoker. The correlation is 0.0. 0.03 and 0.06. Cholesterol. What would you think cholesterol is associated with? Here's cholesterol in this column. Height, negative 0.01. Weight, 0.13. That's actually pretty high for this kind of data. Body mass index of 0.1. Smoker is actually negative. So these are the kind of correlations that you get when you deal with people and attitudes, health information, what people think. Everybody knows that Republicans make a lot of money, except it's not true in the least. So that most of the correlations that people cite don't have anything to do with each other. And in fact, what affects these things most is age. And those are respectable correlations. So that some of these things, because there's 300 observations, are significant. 0.06 can easily be significant if I've got 1,000 observations, like I did in the original data set. And I cut it down just because we didn't need that many. Go back to MyOpenMath, and this time we want perch and brim, weight, length, width, and these are not our perch. This data is from Turkey, and it shows two species. I've got the perch page. I want to look at the relation between the weight of perch, the length, the height. Literally, this is how long is it, how tall is it, and how wide is it. And then do the same kind of correlation. Data analysis, correlation, and it's going to have that old stuff in there that I got to erase. And yours may not do that. It depends on what version of Excel you're using. Input range. I want weight, length, height, and width, including the labels. That's going to do the correlations between length, height, weight, width, output range, pick a spot, and OK.
I got an error that says correlation input.
Look at the correlations between fish weight, fish length, fish width. All of these things are 0.9798, which is what I would expect for the stuff I was using. This is very common when they're dealing with fish in particular, because a fish is hard to weigh. If you try and put it on a scale, unless it's dead, it's moving. So you measure the length. You pull the fish up, stretch a tape out, measure the length, and you can get the weight very, very accurately because they're so correlated. They're so well associated. So that fish length and weight are very common to do. They do this for cattle. It's hard to weigh a cow. You got to march him across some kind of platform, and then they got to stand there. But it's much easier to measure the heart girth, which is the distance around right behind the front legs. You just measure the cow's circumference. And you can actually get a tape that has pounds on it rather than inches because they use the heart girth to estimate the weight. This is also done for deer. Rather than weighing a deer at a check station, they just measure the heart girth. So for that kind of animal, and the relation is different for different kinds of animals, they're using heart girth, circumference basically, of the animal to get the weight. So that these are the kinds of things that actually separate high correlations from low correlations. So it has much more to do with the area you're studying than it does to do with the significance of R. You get enough observations, any R value is going to be significantly different from 0. Keep in mind, when people start talking about the significance of R, they better be dealing in social science because they're desperate. Well, they aren't desperate, that's just what they got to work with. Those are the uses of purely the correlation coefficient. But I still want to predict one thing from another. Like I want to predict weight from length. Here, it's no problem. And if you graph weight and length, mark, well, we want length to be on the x-axis. I'm going to insert and then right-click, and I want select data, and I'm going to mark the length as the x value that'll be on the x-axis. Add x values first, length, and I know it's going to be length, so I don't need to get the label. Then the y values are going to be the weight. And there is the graph of length by weight. And it's a nearly perfect association. I have no problem at all measuring the weight by measuring the length. Here is association purely. I'm looking for ways to estimate something from something else, or to find two things that are associated enough that I can use either one of them. All of this comes down to prediction. And in the MyOpenMath, this is simple linear regression. We are going to predict one thing from another. And I use a scatter plot, and the R value still comes into this, but I'm going to have an X value and a Y. And this is just traditional X and Y. This variable is called the independent variable. And this one is dependent. So I'm going to predict Y from X. So X would be the length, Y would be the weight of the fish. This is simple linear regression. Simple means there's one X and one Y. Length and weight. Linear means it has to be a straight line. I can't use a curve of any sort. All I can fit is a straight line. And the regression part of simple linear regression is just a name. And it comes from one of the first uses of it, where one of the early statisticians looked at the height of fathers and sons. Tall fathers had shorter sons. Shorter fathers tended to have taller sons. So he said that the height of the suns regresses to the mean, goes down to the mean, and the name regression comes from that, and it's still stuck in there. So that it doesn't mean anything except we're predicting something from something else. But we can only have a straight line. And if you look at the fish, if it's still there, it isn't a straight line. It's highly correlated, but if I put in a trend line, and the trend line is linear, you can see that it misses on the low end and on the high end, and in the middle it's below the line. So it's a pretty good line, but I need a line, a linear line. Also, this is exactly what did they teach you about a straight line? What was the equation for a straight line they gave you in algebra class? Y equals mx plus b, or some version of that. M is the slope of the line, and b is the intercept. This is exactly what we're going to do. We're going to make a straight line with a slope and an intercept, except we can't do it the way they did it in algebra class. I've got 2 points, 1 and 5 and 6 and 15, and I want to put a straight line through them. I'm going to get the slope first, the m. What did they tell you the definition of slope was? Rise over run. That's exactly what we're going to do with the regression. It is pure rise over run, and here the rise is 15 minus 5, and the run is 6 minus 1. This is exactly what you did in algebra class, which is 10 over 5, so the slope is 2. To get the intercept, I can go back through the equation and have y, and I can use 5 for y equals 2 times the x value of 1 plus b. The intercept, so the intercept b is equal to 5 minus 2, which is equal to 3. So I have a straight line with the slope of 2 and an intercept equal to 3. And this is exactly what we're going to do with the regression. A straight line with a slope and an intercept. Each of these things has the same characteristics as the association. Here, this one has an intercept of 3 and a slope of 2, which makes it a pretty steep line. The correlation between x and y in this kind of situation is positive. The slope and the correlation coefficient have the same sign. They're measuring the same thing. So that if I have a negative relation, the slope is less than 0 and the correlation coefficient is less than 0. So those two things are linked. In fact, the R value is part of the calculation of the slope. Also, suppose I have fish weight, length here, and weight there, and The weight is in grams. The length is in centimeters. What are the measurement units of the slope? It's going to be a line like this. What is the slope measured in? Rise over run. What's the rise? Weight. The run is length. The slope is in weight divided by length, which is equal to grams per centimeter. So if I'm predicting the weight from the length, then the slope is in grams per centimeter. So I weigh a fish, and I get centimeters. I multiply that, that's the x, here's the m, I multiply that times grams per centimeter. That cancels out, and I'm left with grams, because I'm predicting grams. So these things have an actual interpretation. They have units associated with them. Let's go back to the fish. And we're dealing with perch. And I'm going to show you a trick. We'll get to the details later, but we've got that trend line on there. Right-click on one of the points and go back to Add Trend Line. And you may have to click a couple of times. Add Trend Line. Look at the bottom of this list, down in this part. And right there it says Display Equation on Chart. And when I do that and close it, there is the line that predicts weight from length. The slope is 32.6. That means for every 1 centimeter change in length, the weight changes by 32.6 grams. Excel is written by engineers or computer programmers because in statistics we always write this equation, the intercept first, then the slope, so that the line would be y equals minus 610 plus 32.6 times x. Where is the intercept? Where does that line cross the y-axis? The y-axis. If you extend that line, at least visually, it's going to go down there. The sole purpose of the intercept is to hold the line down, to anchor it. We can't deal with any fish less than 15 centimeters in length because we don't have the data. We don't know what it looks like. All we know is that for the part we're looking at, we get a change of weight with a change in length of 32.6 and the intercept of minus 611 means nothing. It actually means that if the fish has 0 length, it weighs minus 611 grams. So anything past our data, we can't say anything about while we're doing these predictions. Anything bigger than 40, less than 15, we know nothing about. And we can't make any predictions that are reliable past that. This is one of the ways that you can lie with statistics. I can use this line to put in any length I want and get a weight out of the equation. If it's not between the 15 and 40, it's junk. But I can still say it. And this is very common for, unfortunately, education statistics. They will take data that shows some correlation or some prediction and stretch it and then say, little Johnny can't read because he doesn't get enough recess or something. And that kind of thing is very common. And it's something you got to watch for when people are making predictions. What data do they have and where are they predicting? There's more of this that we've got to do, but that's the basic part. And those are the moving pieces. And the correlation is very nearly 1. Even though it isn't quite a straight line, it's awfully close to a straight line. Close enough to deal with.